long the test was going to take to grade. I've graded a total of 2 problems entirely. So I guess a little bit of what I saw. So basically, I graded the first problem and the fourth problem. Yes, I will. So the first problem, the only thing I saw were some mistakes I saw were basically just like RREF, doing an RREF thing on it. There might have been like 1 or 2 mistakes, but like I said, I don't take off much as long as I understood that you knew what to do after the whole thing, right? So if I saw that what you're doing to analyze the system once you got to REF, like this part has to be 0, non-zero, or this part has to be 0. As long as I saw that, you got most of the points, like for that. So I only really took off like maybe 0.1 or 0.2 out of the whole points if you did an arithmetic mistake. So basically you got most of the points on that. Another thing I saw was so a lot of you, when you REF'd it, you guys got like a K and then a K plus 1 or a K minus 1 on the other side. So you recognize that the K had to be non-zero for it to be unique. However, since we had a K minus 1 in the denominator on the other side, you also had to exclude that point from the solution set. So that was another thing. Again, I only took off maybe like 0.1 or 0.2 if I saw that. Because again, I just wanted to see if you guys understood what it meant to find a unique solution, no solution, or infinite solutions. The other thing, the fourth problem. So basically, if you guys put true or false, for example, and you got the correct answer of true or false, and you put some explanation, I gave you almost full credit, even if the explanation might have been not exactly what it was. As long as it was like hitting around the point of what it was, I gave most of the points there. So for example, the elementary matrix one with the determinant, some of you guys said that since the determinant of the entire thing is 0, then A also had to be 0, therefore not invertible. And you put false, so the correct answer was false. However, the reason, like saying for example, that reason I gave, that wouldn't have been correct. However, I still gave most of the points, like maybe took out 0.1 or 0.2. Some of you did see that you had to use the multiplicative property of determinants and know that elementary matrices were invertible, meaning each determinant of those were non-zero, and since everything was non-zero except the determinant of A, and that equals 0, that means A had to be 0. So that would have been the correct answer. But overall, everybody's doing well. Like I see that you guys are understanding a good majority of the concepts, even if like there's might be some things that you're not, I guess, grasping completely. But yeah, so you don't have to worry about the test. From the 2 problems I graded, everybody's doing fine. All right, so now let's continue. Any questions before I proceed? Nope. Okay. Yeah, we do. I just haven't. I spent literally all my entire time grading, and I just haven't had time to do that. But I'll do it soon. All right. So last time we talked about finally what a vector space was, and finally what it meant to be a vector, right? In a more general sense. So I said that if we had these conditions satisfied on some set with some operation called addition and some operation called scalar multiplication. And remember, I emphasize that, yeah, I will. And I emphasize that these additions and multiplications is how you define it to be, right? It's not the same. It's not the same addition and multiplication you're used to with real numbers. As long as that addition and multiplication follow these rules and however you define them, then what you have is called a vector space. And then finally, we said the elements in the set V that we're talking about are called vectors. Okay, so today, basically, we're going to spend a lot of the time looking at examples of vector spaces and what is not a vector space, because those are going to be, I think, a good part of the test that we're going to be doing. So, okay, again, vector spaces and vectors are general in that vectors are elements of this thing called a vector space. Okay, so let's look at an example. So okay, so I guess if you want to, if you look at this definition here, you see how I say a vector space is a triple over a field F. So if your field F is equal to either R or the complex numbers, then we have what you call then the vector space is called a real vector space. And I said or, I guess you can say, or complex vector space. All right, respectively. So, so this is what it means to be what's so-called the real vector space in a complex vector space. In this class, we're gonna basically spend all our time being unreal vector spaces. Okay, so finally, let's look at some examples. So, example 4.2.1. Let's see. So okay, so let's see. So prove that, let's say, the triple B equals Rn plus n times, where the whether the plus and the multiplication is the standard. Addition and scalar multiplication. Yeah, is a vector space over R. Okay. So now let's discuss on how to actually do this. So literally, all you have to do. Okay, so what I mean by the standard addition and scalar multiplications, I just mean the standard addition of vectors, how we defined it, and the standard multiplication of scalars and vectors, right? All right, so how do you prove that this thing right here is a vector space? Well, literally all you have to do is go and check every single one of these like a list, right? If you can check every single one of these as like with the lists, then you basically prove that this thing is a vector space. Now, if you remember, I spent some of last section doing this part right here. Theorem 4.11, right? So do you see how this one is basically almost, well, it is identical to the conditions here, right? So what we did, what I basically said here in theorem 4.11 is I proved, you basically said that Rn is a vector space under those addition and multiplication. So yeah, so solution. So let's resize this. So solution, oops. Or I guess I'm better yet to say proof. So we need to check all, I guess you could say 10 axioms for a vector space. So, but by theorem 4.1.1, all of them are checked. For Rn with the standard addition and multiplication, right? So again, this is why we call Rn a vector space. So that's why we call every like element in Rn or even R2, R3 vectors, because it by definition this whole space is a vector space. So that means how we define a vector space, every element in there is a vector. Now it's very like I said. So a lot of the properties that come from the addition and multiplication, you can visualize them as arrows and stuff like that, which is true. That all that is true as well. But not but that doesn't always carry over to other types of vectors. Well, almost. I mean, in that sense, there is. I guess every finite dimensional vector space is isomorphic to a copy of Rn, but we'll talk about that later. Okay, but for this example, that we already proved it last section, right? So now let's look at let's start looking at more examples that isn't just your standard Rn. Okay. All right. So let's look at let's take a step up now. So it's not too hard, but it is different. So prove that the set of all 2x3 real valued matrices under the standard addition and multiplication of matrices, and I mean scalar, not actual multiplication of matrices, is a vector space over R. So by the way, again, to ask you guys, what do I mean by this over R? What does this mean again? Hmm? Yeah, it's the field. So, but why do we need this field? Like, what's it used? What do we use it for? So, where do we get our scalars from? The field, right? So when I say over R, that means our scalars are going to come from R. If I say over Z, that means you're going to get your scalars out of Z. If you get your and so on and so forth, right? So this over R isn't always true. Like I could have said over the rational numbers. That means your scalars are going to be coming out of your rational numbers. Or I could have said over what's another field? The complex numbers. Then my scalars will be coming from a complex number. So that's what this part means, okay? So whenever you take a scalar, always look at this over whatever. And that's where you're going to be taking your scalar from, all right? Don't always take it from R, okay? Okay, so solution, or maybe some more big proof. So let's actually prove this. Okay, so what is the first thing we have to check? Well, if U and V are in my set V, then the addition also has to be in my set V. So here, what is my set V? This thing, right? This is my V, right? So pick two matrices A and B in my, there are 2x3. Okay. Now I just have to show that when I add them together, it also lands as it also lands in that set B. Or in other words, if I add them together, they also become a 2x3 matrix with real entries. Okay, so let's do that. So A1 1, A1 2, A2 1, A2 2, added to B1 1, B1 2, B2 1, B. Okay, if I add them under, so how did we define matrix addition? We defined it to where we add entry wise, right? So A11 plus B11, A12 plus B12. Let's see, A21 plus B21, A22 plus B22. Okay, question. Is this a 2x3? It's not. Oh, sorry. Let's make this a square. This yeah, my bad. This maybe a 2x2. Let's just do it that way because I completely messed up. So is this okay? So I picked 2x2 matrices that are 2x2. Is this a 2x2 now? Yes. Yeah. So yeah. So this is again a 2x2 real matrix. So it has closure, right? So this first one is checked. All right. So number 2. What's number 2 now? Do matrices commute? Meaning if I take A plus B, is that equal B plus A? Yes, under addition it commutes. Multiplication it doesn't. Yeah, for sure it doesn't under multiplication. So matrices commute under addition or matrix addition. So this one you don't have to really check. I mean that's a little bit redundant. First one you probably do have to check though. That one I do want you to check. So 3. Okay, number 3. Can you associate matrices? If you had 3, A, B, and C, does A plus parentheses B plus C equal parentheses A plus B plus parentheses plus C? Yes, exactly, yeah. We also know this. Matrices, well, I should say real valued matrices from you. So real valued matrices associate. Okay, I mean, okay. So quick question: would you guys actually know how to prove that? Like, if you were to prove, if I told you to prove commute matrices commute, how would you formally show that? I mean, it is true, and you can show it with examples as well. But like, it does only examples. So how do you actually show it for every matrix? Well, if you add them, so look at number 1. I added these 2 matrices, right? And each entry right here, that's what they gave me, right? Now here, the addition here, again, is different from there, right? The addition there is actually for real numbers. We know that real numbers commute already. So there you can just commute them. So you can rewrite this as B11 plus A11, and then B12 plus A12, and then separate the matrix that way. So you use the fact that real numbers commute under addition and then separate it that way, okay? So that's why I said that you don't have to show it because it's kind of obvious, but I just wanted to be sure you guys were, made sure, I just wanted to make sure that you guys knew that. And same thing with associativity, right? Real numbers associate under real number addition and yeah, real number addition. Okay. So number 4, as you guys can see, this is going to be a pain, but whatever. So number 4 says there exists a 0 in V such that for any V in V, V plus 0 is V. Now, in this set of matrices, 2 by 2 matrices, does there exist this 0 such that if I pick any other matrix and add it to that, it gives me back the matrix? Yes, and what would that be? Yeah, a 0 matrix, right? Matrix is 0 entries, yeah. Even if we don't have value C, which C are you referring to? Uh, are you looking at the ones below, or so number 3 is just to prove associativity, right? Oh well, so the W is for this one you would just pick 3 matrices. So there I just picked V, U, and W. Here you would just say pick A, B, and C. Matrices A, B, and C, and C would be your W in that case, right? And then you can show it that way, as associates in that way. Yeah. Okay. So 4, yeah. So yes, if for 4, yes, pick this 2 by 2 0 matrix. Then for, let's say, A in the same we know that A plus the 0 matrix is just going to give me A. So that one's also, so there does exist this element 0 in my V that does this. All right, perfect. Number 5. I promise I'm only gonna do is come once, just once, and then the other ones will just state what these things are. Uh, so 5 for any V. So for if you pick an element in the set V, there exists another vector V that's denoted negative V, such that that V plus negative V is 0. So for matrices, does that exists? So if I pick a matrix A with the entries A, B, C, and D, does there exist a matrix, say, I don't know, negative A? Well, I mean, that kind of, it already tells you what it is, but there's exists a matrix B such that A plus B is 0, right? It's just, you just take the entries to be negative, right? So pick, let's say, so let's just say let A be a 2 by 2 matrix where, let's say, A is equal to A, B, C, and D, right? So pick A and, oh, sorry, not A, let's say B with B is equal to negative A, negative B, negative C, negative D. Then obviously we have that A plus B is equal to 0, right? Or the 0 matrix in this case. So yes, this one is also good. So this one's also satisfied. Okay, so number 6 now. If alpha is in my field and V is in my set V, then alpha times V is also in my set V. Okay, so again, where did I pick my alpha to be in? Yes, exactly. Perfect. That's what I wanted to make sure you guys understood, know that. So yeah, and here in this case, we picked alpha to be my real numbers. And A to be, okay. So what's the goal again here? Well, does alpha times, let's say A, which is A, B, C, and D, is how do we define it? We defined it entry wise, right? Now, is this thing that I just took, is this also a 2 by 2 matrix with 0 entries? Yes. This is also, so perfect. So this one's also satisfied. Okay, just 4 more. So 7, uh, does my alpha distribute? Uh, well, I guess that one's not too obvious, but it does. So actually, that's a pretty good point. So how do we? Okay, so pick. So let alpha be my real numbers again, and just say A and B be in my. Does alpha times A plus B? Okay, so we can't just distribute this alpha in. This multiplication, we don't know if it distributes, right? So what would be the correct approach to see if it distributes? And let's just say A and D has, I guess, this form A, B, C, and D, and then B has E, F, G. I don't know that. Okay, so we had these two, right? So yes, I do. Every time I forget what the next letter, I always have to sing it to see what the next letter is. It always happens, but it's fine. All right. So what do you think we should do first to show that this thing distributes? Because remember, you can't just distribute it in. This multiplication is not the same as real numbers. Yes. Yes. Perfect. Exactly. So add A and B together first. Then you would have A plus E, B plus F, C plus G, D plus H. Okay, now we have a single matrix that we know how to apply this multiplication to. So now we have alpha times A plus E, um, alpha B plus F, alpha C plus G, alpha D plus H. Okay. Okay, now can you distribute this part right here? Yeah, right, because now that multiplication is multiplication of real numbers, which we do know distributes. So this is this, and this is this. Okay. So now you can separate it out as two matrices. Plus alpha. Oh wait, confused myself. B, C, and D. Right, and now just reverse that multiplication definition, or just factor out the alpha, I guess you can say. So alpha A B C D plus alpha E F G H, and that was just, so it also distributes. So okay, key point. Don't just distribute the the scalar in with how I define the multiplication. Like if I give you on the exam some rule for the multiplication, and you're checking this part, right? Don't just distribute it, because that multiplication is again not the same as real number multiplication. You you would have to do basically what we did right here, right? We would have to first add, then do the multiplication, and then see if that distributes or not. Okay, so all right, so 7. Let's do 8. Same thing. I'm not going to do it, but it's so number 8. So it's using same argument as in 7. Alpha plus beta times A is equal to alpha A plus beta A as well. Okay, you would just do the exact same thing for that one. 9. So number 9 again is the same thing, using same argument, similar. Well, I guess you say similar argument. Alpha times beta times A is equal to alpha beta times A, right? You would just have to do this one first, and then do the alpha, then you'll see that all this works. And then 10, one times u is equal to u. So pick 1 in the real numbers in this case. So 1 times A is definitely just equal to A, right? Because every entry is going to multiply by 1. Real 1 times any real number is that real number. Okay, so is a vector space over R. Okay. Okay, perfect. So that means that the matrices are now considered vectors in this case here, right? So again, so remember these. I guess you don't think of this matrices as vectors anymore. I mean, as arrows anymore, right? However, there is a concept again of a. So it might seem like kind of weird, but you know how normally in Rn you would have the notion of the length of a vector, right? Because you think of it as an arrow. Well, you also same thing here. You can also think of there is a notion of what is the length of a matrix as well. You would that's what you would actually we'll talk about it later, but those are like called norms of in a vector space. And even more, you will talk about inner products, which is actually you can define in a few ways, but you can take it as a square root of the norm. So no matter what the object is, you can always define a notion as a length, even though it doesn't really make sense, or you can really think of it that way. Yeah. Okay. So this one's one step up. However, we have to take it up a little bit more now. So we're going to look at a different vector space again. I'm not going to check every single axiom for this one, but we are going to take the notion one more step up because so we still need one more because we're going to talk about a certain vector space that's pretty much going to be very important to us. Okay, so here, so let's define a notation first. Let S be a set. Okay. And say F is a field. Okay. Denotes the set F to the S. So this is just notation. Doesn't mean I'm raising this set to some set power. We're going as this. So it's going to be the set of all functions from S to f. So all you can think of it as, again, all functions from s to f. So again, what does a function mean again? You've taken, it's just a rule, right? Like f of x equals x squared for real numbers. To the real number 1, you assign the value 1 squared. To the real number 2, you assign the value 2 squared, in other words, 4, right? So it's just, you can think of it as like a rule that assigns a number to another, well, and in real numbers, that's what it is. But you can think of this one as the function is, the functions are rules that assign an element of S to another element in the field S. So it's just like you can think of it like, so if, let's say here's my S, and here's S1, and here's my F. The function f just assigns this S to, say, f of S1. That's right here, right? So it just, you can think of it, it maps S1 to f of S1. So now I'm basically what this f to the s it means is it's the set of all those such rules, right? So it's not just one function, it's every single function that you can possibly conceive of, okay? So I'm forming the set now, okay? Okay. All right, so now what am I doing this for? Because again, this is the next level that I'm talking about. I have to take the level abstraction one more step before we can talk about the other stuff that we need. So let's define addition in the following way. So I guess you can say if f and g are in this set, or two functions here that go from s to f. Let's say f plus g evaluated at x is, again, just f of x plus g of x. So just in college algebra, remember we defined it this way. So this is how I'm going to define addition on the set. So for, let's say, lambda in my field f, let's define f lambda times this f of x to just be lambda times f of x, okay? And this multiplication comes from the field. Remember, a field carries a multiplication with it, but you don't have to know that. Just remember these two, okay? Okay, so now you can see what's going to come next. So the next example. So what is the next example? Well, the next example is going to be this. 4.2.3, prove that this thing right here, this triple, is a vector space over F, okay? Okay, so I'm not going to prove every single one of them. I'm just going to pick the important ones from the axiom, from the list of axioms. But again, if you want to prove it, you have to show all 10 themes, all right? All 10 themes. So let's see. Okay, so we're going to show this first one, this one right here, and what's the other one I need? Let's see the other one back. So we want that, yeah. So and then this one right here, yes, this one. So these three, 1, 4, and 6. So I'm just going to show you those three, and then we'll move on to the next thing that we have to look at. Oh, goodness gracious. So let's just, I don't know, prove the first three. So 1. So pick, let's say F and G in my set, in that set V. We just now have to prove that this thing is also in the set V, right? So yeah, so for sure. Okay, so we have F plus G, right? Evaluate some X. So this thing goes from S to F, right? So if I plug in, okay, so sorry, so each one of these individually goes from S to S. So this is, again, was defined as f of x plus g of x. Now remember, from that little picture that I showed you right here, right? Where does this thing land in? Like, I mean, it's so I mean, let's say this was my x, and it went all the way over here. Where did it land in? I mean, it's not a trick question. It's just it's in the picture, right? It landed in F, right? So this landed in F, and this also landed in F, which means that this entire thing went from S to F, which means that this is also an F in S. So okay, so all right, guys. So we maybe should stop right here because we need to, because again we're gonna create the vector space of continuous functions and polynomials as well, because that's gonna be an important part of the section. Does everybody see why these f of x and g of x landed back in my f? Yes? Okay. So, and does everybody see why then the entire function maps from S to F? Because if I took something in S and it gave me something in F. And now this addition is, okay, so maybe I should, this addition is defined in F, right? So remember, and maybe that's a little too much, but adding two things in F also lands you back in F. So this has to be in F, okay? So that's the first thing. Next thing. So what was the next thing I wanted to say? 4. So 4, so let's say 4. Does there exist a 0 such that, so let's see. So I want a 0 such that, yeah. So does there exist a 0 in, so does there exist a 0 in this f of s such that f plus 0 is equal to f? So again, so I want you guys to understand this, because again, this is going to come back to when we try to create the vector space of continuous functions and polynomials. If you look, let's say over here, where is it? Right here. So remember how I gave this informal definition of a field, and I told you that this thing always has to carry a 0 in it, right? So again, this is the same technique that we're going to use for the continuous function case. In this case, it's yes. Why? Because just pick the function. Let's say, I don't know, let's call it f0, that maps everything to 0 in f. In other words, f of x, f0 of x is equal to 0, right? So if I do the addition, so f plus f of 0 at x, well, this is going to be f of x plus f of 0 of x, which in this case, this thing is 0, so this is just going to be f of x. So that thing does exist in here. So remember this, right? Because this is going to be important to the example that we're going to do for continuous functions. And then let's, oh, sorry. Yeah, so, and then scalar multiplication. So number 6. Okay, so pick an alpha in my field and f in my set fs, right? Yeah, I'll go back. Oops, I'm going too fast. Okay. Here, okay, so I guess I can just keep talking a little bit about this. So for, let's just say I told you I was trying to look at continuous functions. So do you guys remember what continuous functions meant? It just meant, it's just informally just say that it's a function that I can draw without picking up my pencil, right? Let's just say that. For there is, if I pick a continuous function f, for example, does there exist a continuous function such, say g, such that f plus g equals f? I mean, it's the same case as this one. And let's say my continuous function is a real value. So it goes from r to r. Same thing, right? I can just map everything to 0. So pick the continuous function that is identically 0. That's a continuous function, right? I can draw the horizontal line on the graph without picking up my pencil. So now if I pick g to be this function, the 0 function, then f plus g is 0, is f, right? So in this case, we found a function that acts like the additive identity, right? So that's why I was doing this for you guys. Yeah. So you pick it. You pick f0 to be result in 0. Yeah. So you pick this. Yes. So I picked it because remember, you have to find something in your set such that you pick a function, add it to this function, it gives me back that function. And I picked it to be this guy. Okay, so okay, so now for this one. So let's do f times this. Well, now this is going to be alpha times f of x. So both of these things are in f. And then this multiplication is happening in f. Remember, fields have, I gave you that definition is closed under fields, right? So this thing also lands in f. So this thing entirely just goes from s to f. So that means that alpha times f is in this set as well. So it's closed under the scalar multiplication. Okay. So those are the 3 important ones I wanted to show you for this one, because now I want to show you the concrete case, right? So the continuous function case in this case. Let's see. So let's do that. So let's see. So denote C from negative infinity to infinity to be the set of all continuous functions on negative infinity to infinity. Okay. In other words, C from negative infinity to to infinity is equal to, so f from, I mean, you can just say r to r, such that f is continuous. Okay, so it's all the continuous functions that you can ever think of. So I don't know, like x squared is in this set, the sine is in this set, cosine is in this set, e to the x is in the set. Okay, so all the continuous functions is what makes up this new set. Okay, and the addition and multiplication I'm going to define in this set is the same as I did right here. So these two. These are definitions right here, right? So those are going to be now called, I'm going to call them the standard addition and multiplication on functions, okay? And so let's do the example. 4.2.4, prove that c negative infinity to infinity plus and this is a vector space. Okay, so we're gonna go through the list. Okay, so if I add two continuous functions, is that result a continuous function? I think you might have mentioned it like in Cal or. Okay, so if you add two continuous functions, the result is a continuous function. So just assume we know this. Okay, so the first one is satisfied. If I have a continuous function and I multiply a real number, let's say over r, and I multiply a real number on it, does it remain continuous? Right? Yeah. So that one's also satisfied. Again, if I have a continuous function f, does there exist a g in my continuous functions such that f plus g is equal to 0? Yes. What is that one? Just negative f, right? And we already said that multiplying constants on f makes it remain continuous. So so negative f is definitely in that set. Real numbers distribute on my continuous functions, and so on and so forth. So in this one, I'm not going to show it because I'm running out of time anyway. So solution satisfies all axioms. Okay. Okay. So that now here continuous functions are vectors in this case. Okay, guys. So just a few points. It might seem like no matter how you define it, everything's just going to become a vector space. But next time I'll talk about things that aren't vector spaces, and then we'll move on to the next section after that, to subspaces. Okay. So where all this is leading up to is basically, I know it seems like it's super abstract at the moment because it is pretty abstract, but we're basically we're leading up to what's called maybe some applications like minimizing best fit curves on like data. Like if you have a set of data, you want to find a polynomial that like fits it well. Well, you can use the fact that the space of polynomials are create a vector space, and then you can define a norm on it. Then you can find this model that like makes it nice and neat and fits it pretty neatly in it. So yeah, so we there is a point to all this. It isn't just all abstract. All right. So any questions? Yeah, this one. Okay. No questions. You? Okay. Gotcha. Okay. No questions. Yeah, I'll open it up. So you can still put it in, and I'll update it. So you can, yeah, so you definitely, you can just, but I mean, like I said, if you do all the homework from web and you should still be fine. Like this is the class anyway, so yeah.
Thank you. Is there a due date on the podcast?
I know it says it might be, but no, you can just post, yeah, just post it and I'll update all your
Okay,
things.
thank
Yeah,
you.
yeah.